Okay, so we're going to be looking at using the laser transit to find elevations, relative elevations in the landscape, particularly as pertains to rainwater harvesting projects. This is a skill that in general everyone in landscape should have this skill, but particularly it becomes important with rainwater harvesting projects where we're measuring to the inch the flow of water, where water's going to go, and modulating the flow of water by earthworks that will be very precisely sited at elevations to control the flow of the water. So the way we do that is we use a transit, and setting up a tripod for a transit is a very easy matter. It sometimes helps that the laser transit unit has its own leveling device, so it will find level on its own, but I find it's better to pre-level the tripod. It makes less work on the unit in leveling itself, and the closer to level you have the tripod to start with, the easier it is for the unit, the transit, the laser transit unit to find its own level. So first way, with a tripod, you can always find level with a tripod by setting a level across the tripod and finding level one side to the other. Now that's pretty level. We might want to lower that a little bit on one side or the other, but you can see the bubbles tracking right in the middle of the indicator. So that's telling us that that's leveled sideways this way. The next step is to rotate that 90 degrees and look at the other way. You won't be able to see that angle, but from here I can tell that in order to bring the bubble to the middle, I have to move backside up a little bit by bringing that one leg in. So now the bubble is in the middle this way, and the bubble is in the middle this way. So our transit is basically leveled. No matter which way you spin the level, you get roughly a level surface on the top of the transit. So that helps the machine not have to do so much leveling on its own. So now we'll attach the laser unit. Here's the laser transit unit. Put it onto the tripod. Attaches with this screw unit underneath. Fix it to the tripod. And there we go. And when we power up the laser, it'll start to find what's level, and the sooner it finds straight up and down level, the faster it will level itself out and start to spin. So it found level, and now it's spinning. What's happening is that little laser beam that's mounted in the head is spinning around in a circle in a level plane. So what it's establishing is a level laser tabletop, if you will, a level plane that is perfectly level and extends out as far as the laser can see. So now with our receiver unit, we can activate the receiver unit, and then as we move the receiver through the field, we can detect where that laser beam is. We get a slow, steady pulse if we're below the laser, and if we rise above it, we get a fast pulse. So finding the beam is a question of moving the laser receiver so we're right between the fast and slow pulse. It'll light up green if it's exactly on the laser. So this allows us to detect that laser beam no matter where we are in the landscape. The final part of the picture is we use a measuring stick. And with the measuring stick, we can tell exactly how far below the laser any given object that we want to get an elevation on is. So by detecting here, fast pulse tells us we're high, so we're going to lower. Now that we get right there, That's about where our indicator is, and it shows that we're right at 5 feet. We're just slightly above 5 feet at this point. So this sidewalk here is at a relative elevation of 5 feet below the laser plane. Now we can go elsewhere in our landscape and figure out where we are relative to the laser plane. So it'll tell us if one place is relatively higher than another spot in the garden and in the landscape. So it helps us to determine exactly where to set spillways and sills for rain earthworks, and also helps us to be sure that our pipework is falling from across long distances, is falling appropriately across the length of the pipe. So we'll go ahead and do some elevation checks around in this rain garden here, and see how the laser transit helps us to find the relative elevations. Here we are in the Lifescape garden looking at the rain tank system. This is a utility shed that is part of the maintenance department of City College, and we are collecting the water from the roof of this utility shed. And you can see where the gutter and downspout come down, go through this rain head. This is a leaf screen here that's meant to screen out any heavy debris that would be coming off the roof of the shed. So any leaves and things that are in the gutter will get trapped by this screen, and the water will fall through into this pipe. Continue on over and into the top of our rain tank. This is a 2,500 gallon rain tank. You can see it has marked demarcations. Here's 1,000, 1,500, 2,000, and I believe the very top is at 2,500. So it's a 2,500 gallon tank, and this pipe is flowing into the tank. So when it's raining and water is flowing in, the tank will be filling. Once the tank fills to this point, water is going to back up in this pipe, and as this pipe fills and it gets to this particular spot here, this is our overflow. So once the tank is full and water's backing up in this pipe, it'll back up to this little hump here, and once that elevation reaches that point, it will start to spill down this drain pipe and be overflowing into the landscape. This is a strategy for overflow from rain tanks. We call this inlet is the outlet strategy. So you're basically just, it leaves less plumbing into the tank when you can use the same bulkhead fitting for the inlet and the overflow outlet, basically by generating a passive overflow system here. So as the tank gets full, water stops entering the tank and simply overflows down the drain pipe. So what we're going to do is take a look at the relative elevations of the drain pipe as it makes its way into the garden. We're going to use our transit again to just verify that this pipe has good fall as it goes across into the Lifescape garden. That's an important aspect, and we want to just verify how many inches difference we have over the about 20 feet that we have before the pipe daylights into the garden over there. So we'll go ahead and take the laser sensor here, see if we get a signal. There it is. So measuring at basically what's the pipe sitting on the ground here. So I'm going to take the ground level right at the base of the pipe. So this would be basically the bottom of the pipe. And let's see where the ground registers there. It's coming in right at just over, it's 5 foot 1 inch and 1/4. So that's where we get the shift from slow to fast. It's right there, and if we're lucky, a green light means we're right on it. But you'll mostly just surf between the fast pulse and the slow pulse to find exactly where there's the spot right there. So it's just at 5 feet, 1 inch and 1/4 of an inch. So 5, 1 1/4 is our elevation here. Over on the sidewalk, we had an elevation of 5 feet even. So this is 1 inch and 1/4 lower than the sidewalk because the stick is longer. Our laser plane is staying level, and we're measuring downward, and we're finding that at this point the surface of the ground is 5 feet 1 1/4 inches below the laser plane, whereas the sidewalk was only 5 feet below the laser plane. So that means that this spot is 1 1/4 inch lower than the sidewalk that we measured first. So it's sort of counterintuitive that the higher number means something is lower in elevation, but remember, we're measuring down from an established level tabletop, essentially a laser plane. So we're measuring down to the ground, so the longer distance it is from the laser plane down, the lower that space is. So the higher number means it's a lower elevation. So this is 1 1/4 inches lower than over there, but let's see where the end of our pipe, where the pipe comes out. Let's see how much lower than 5 feet 1 1/4 inches. Let's see how much difference is between this spot and that spot. See how much lower the pipe is at the other end of the pipe. We're going to take a look at the outlet from the pipe that comes from the overflow from the rain tank. And that pipe, you can actually see the rain tank in the background there. And our overflow pipe, which comes down into the ground, passes under this little section of pavers and comes out here into the garden right here. And you'll have to forgive the condition of the zone. It's been hasn't seen a lot of attention in a while, so it's just a little overgrown with weeds and a little full of debris, but basically the system is still intact. And what we see here is the outlet of the rain pipe. That's what I wanted to check the elevation of, to be sure that it's below the 5 1 1/4 measurement that we made on the other side. But you can see here there's a little rock basin, so that as water flows out into here, it's armored with stones so that there won't be erosion. We've got some small gravel in the bottom to just armor the bottom of that, and water's going to flow on out into this earthworks channel which we created here. Again, it's a little overgrown with weeds and leaves, but that really doesn't matter. The earthwork will function whether it has weeds or leaves in it or not. That's the beauty of these rainwater harvesting earthworks. When they're well constructed, they persist in spite of buildup of organic material. This is all stuff that will decompose as water comes into the system. So water will enter this basin and flow into here. We brought this basin over toward this avocado tree so that the avocado tree would benefit from the infiltration here in its root zone. And what we constructed here at the far end of the basin, this is the basin, the deep spot, and then over here we constructed a sill, a little rock sill. This is essentially a little check dam that as water flows into this basin, it'll stop here in the basin and pool during the time that there's water flowing in. It'll hit this little sill and pool in this zone and infiltrate in as long as there's water in the system. And Keith is our little supervisor dog. He's doing a great job supervising. And so the reason for the armored check dam is to cause a little pause in the water here. We want to slow it down as it flows through the system. So check dams and sills are important to modulate the flow of water through the earthworks. And that's why we've got this little rock dam there. So we'll do next, we'll follow downstream. As we go over this little rock sill, we continue down into another basin on the other side. Another opportunity to infiltrate in the root zone of the avocado tree. And as we come around, we have a little final basin here and a final sill to our basin here. We've set a rock at just the right elevation here to allow water to pool in the basin to maximum effect and then spill over and into the lifescape garden ultimately when it's done infiltrating in these basins. So let's do some elevation checking to just see where our inlet and our spillways are set, so that we kind of know how we're doing on our on the flow, how water is going to behave when it's in this system. So here we are at the outlet pipe. We're going to check the elevation of the outlet pipe. Now I'm putting the meter stick right there at the floor of the pipe, so we're measuring the bottom of the pipe like we did on the other side. And let's see where this comes in when we do our laser sensor here. Let's make sure it's on. There we go. There we are. So fast pulse we're too high, slow pulse we're too low. So there's that boundary between slow and fast, and it comes in right at 5 foot 7 inches. So 5'7" is quite a bit below 5'1" and a quarter. So we can see that there's almost 6 inches of difference between this side of the pipe and the other end of the pipe. So that over a 20-foot run, that's plenty of fall for water to move right on through that pipeline and come gushing out here on this side. In fact, I'm pretty sure that when this pipe was set, we were careful to set the pipe as high as we possibly could because we didn't want to squander any fall along the way. We want to keep that pipe as high as possible so that we can do more with it. The higher the water is, the more places we can get with it. So as you're running rain piping, never give up fall that you don't need to give up. For example, you could put the pipe deeply under the pathway, but that would make it deeper over here on the outlet and would mean you'd have to be deeper everywhere else. So the more height you can preserve, the more elevation you can preserve along the way, the better off for your system. So never squander fall when you're laying out your pipelines for rainwater harvesting. Keep everything as high as you possibly can. This is true in gray water plumbing as well. Gravity-based flow systems for gray water and rainwater. You always want to conserve fall wherever you possibly can. Never squander the fall in a rainwater system. So we figured that this is 5 3/4 inches deeper. It's the number is higher by 5 3/4 inches. So that's how much below that point over there we are on this side of the path. Let's check and see where some of our other spots are. So here's our mark. Let's see what we get. Now that we have the tree branches out of the way, we were at 5'7", so we expect to be below that. There we are. So we're just at 5'7 1/4. We're just the measurement is just above 5'7 1/4. So we're basically at this sill here, we're 1/4 of an inch lower than we were at the outlet of the pipe. So any water that comes out of the pipe is going to come to this sill and flow over with a 1/4 inch difference between that and here. If this check dam were to back up in some way, water would begin to rise at the base of the pipe, but still basically be below the pipe, so that we're not going to impede flow through that pipe at all by backing up water into the pipeline. We want to keep our sills downstream just below the inlet pipe so that water flows through the system. But that's just about perfect right there. Thanks a lot, Lewis. So now let's check the final outlet. Check the sill on this final spillway, this rock that's set here. Let's see what our final outlet is going to do. So the final outlet is at 5'5", which is higher than our inlet, which was at 5'7". So the measurement's shorter, so it means that this sill is actually 2 inches higher than our inlet pipe, which I would prefer to see this sill a little lower than that in order to release this system so that we don't back up water to the pipe, but it's actually not necessarily incorrect to do that. By keeping the sill as high as possible, we're maximizing the amount of water that would be retained in this basin. One thing we want to watch out for, though, and I noticed this earlier, is that this edge of the basin, we had intended to build up with these rocks, and that never happened during our landscape construction class. You can see the leftover rock that never got put into the system. And if you look over here at the ground, you can see where the rock armoring of this last back berm of the basin never got completed. So it actually ends up that this spot here looks to me to be the lowest point of the basin. Let's verify that and see. Yeah, that's reading at 5.6. So it's just below our, just actually still an inch above our inlet, but it's also an inch lower than our 5.5 measurement that we got on the sill going out. So so this would be a lower spot. 5.6 is lower from the laser line than 5.5. So that means that our sill actually wouldn't function. Water's going to leave this basin over here. So this is an issue that should be addressed. These rocks need to be incorporated into the back end of the basin, and this berm needs to be built up so that it's higher than the spillway with a good little margin for error. We want to have what we call freeboard on the basin, which means a little area of earth that will stay dry above the water line. That's called your freeboard, and typically you want to have several inches of freeboard above the water line when you build a berm, just to keep that berm solid and stable. So this berm back here needs to be built up. That's what these rocks were intended for, but you can see how the project kind of stopped before it was completely finished. But that's important to know when you're trying to look at situations like this. By telling the elevations, by shooting the elevations, you can predict what the water is going to do. And we know that the water is going to go out here in this low spot rather than go over the sill. That's not a huge problem. The sill just guides water into the garden there, and this is exactly in the same location. So the water's not going to go anywhere different than it would. It's just that this is not armored with stone, and if water starts flowing out of this, it's going to scour the earth down, and we could have some damage to the earthworks by the scouring of the running water. Whereas in an armored conveyance with rock, the purpose of the rock is to stabilize the conveyance so that you can have flowing water going through the conveyance and you will not have erosion that will compromise the earthworks. So it's important to armor with rocks in places that you're flowing, and it's also important to shoot and be sure that your sills are set appropriately. This sill probably should be lowered a little bit to be most effective. I'd rather it wasn't 2 inches above our inlet. But again, still not a huge problem. Just I would lower this sill just a little bit and build up this basin here, build up the berm here on the downside of the basin. Okay, that's our little rainwater system here in the Lifescape garden.